Yeah. So to begin with all that, we have to consider the two ways to solve a problem in computer science. On the one side, we have traditional programming, where a software engineer writes the code, the rules that the program should do, the solution it should get. Often a solution is created based on input data and kind of that the roadmap of how to get to the solution is written by a human in a programming language like Python. So the ingredients for this way of solving a problem is there need to be the human generated rules. There needs to be data that's kind of the grounding for it, the content on a web page, numbers in a calculation, etc. And then you get answers that people can use. You get software products. I mean, the software industry is really huge right now, and something maybe 50 years ago was unimaginable. And I feel like that's also something that will happen with AI. The software industry will become more and more, will become greater. But I don't think it's a bad idea to study computer science because it will become even more relevant. However, I think software isn't exclusive to these huge software giants like Google or Microsoft. So you may be thinking, you've probably all heard of vibe coding, and this is actually still in the um, eh, is part of traditional programming. The human is just replaced by AI, and the AI writes the code. But to have an AI in the first place, you need to teach a computer how to think and how to make these predictions. And that's exactly what machine learning is. It's the process of acquiring knowledge, kind of, it's the school for a computer and for the AI that will hopefully become increasingly better. So you have rules and you have data. But these rules, they are implicit. They have never been defined. For example, um, there is no rule how, for example, a model like ChatGPT it wasn't given a rule of how a language works, how the grammar works, what words have what meaning. Um, it discovered that itself. And the basis of machine learning and is data. And data obviously is also a part of traditional programming, but in machine learning, the data is the foundation and everything builds on top of it. And the more data you have, that better your model will become. Obviously, you also have to have a good model architecture. For example, the transformer that is ChatGPT or general pre-trained transformer, that's I think a discovery made at Google DeepMind that allowed for these large language models to exist. But then you also need the computing power. That's why so many data centers are built. And I mean, the companies like Microsoft with Azure and Amazon with AWS are making tremendous efforts to expand their data center capacity for companies like Anthropic or OpenAI to train the best models. And you may have heard there are even companies like SpaceX, but also there are other startups that want to build data centers in space because the more training capacity you have, the better your model will eventually become. And that's also kind of what is called the bitter lesson, meaning that many people, many uh, many people want to um, use their own thinking, like um, their own rules to make a program better. But in machine, uh, but for machine learning, these human-made rules are less important than just increasing the amount of data. And that was kind of the paradigm shift that led from very basic AI models to these very capable ones we have today. And as you see, the rules are generated by the machine itself, and the answer that's in parentheses, and I'll explain why that is on this slide. There are multiple types of machine learning. There is supervised machine learning. That's what we'll cover mostly today. Supervised machine learning learns from labeled examples. So you have the data, but you have the solution to the data next to it. So you basically just have to use an arrow that guides the, the machine from the start to the end. And it learns the rules kind of, the rules aren't written explicitly, but by having the data here, the result here, it's pretty easy for the data to see a pattern and predict new outcomes on new data. So this could be, for example, used in email spam filters. So it's either spam or no spam. So it's kind of a binary problem. And you have multiple inputs that influence whether a message is likely spam or not. But that means the model kind of gets a lot of examples of messages that are clearly spam, clearly not spam, and then when it is applied in the real inbox, it will predict the whether it's spam or not spam on this new dataset. There is unsupervised learning, probably the most interesting one, but it's more complicated. It uses, for example, neural networks that can get very complex in deep learning to find the hidden patterns in data that have no labels. So there's no result to the data, how it should look like. It's just, for example, you feed the AI a lot of text and it has to figure out how the language works, but also kind of what has to figure out the whole knowledge base that humans had. And that is used in large language models like ChatGPT, Claude, Gemini, etc. There is also reinforcement learning. And this is basically learning by trial and error. So you can have a success or you can have um, a, a, a bad result, an error, and you basically guide the system through that. And rewards mean the system tries that thing more often. And if it was a bad move, it does that move less often. That's the most famous example is AIs that can play chess or Go, but they are very limited to one aspect of like just that game, and they aren't general purpose AIs and for general purpose AIs. Unsupervised learning is the most important part, but obviously in models like if you're using ChatGPT, there is also yeah there are also these supervised and reinforcement learning aspects in them. Let's focus on supervised learning. This is, for example, image classification. You give a lot of images of cats and dogs, and then you train it on massive data sets, but they are labeled. So you see here, that's a cat, that's a dog, fine. But what if a new image comes? And this is kind of the input. It's like in a function in mathematics, you have the variable x, and x influences x plus some parameters, some weight and bias will influence the outcome, which is f of x, the function. And in this case, obviously, the input is a cat, an image of a cat. So the prediction should be it's a cat. But these systems obviously can make mistakes, and we'll look at that later. For unsupervised learning, as I said, most prominent example is large language models. And so if you have a sentence like the cat sat on the blank, and then in the corpus of text, probably the cat doesn't sit on a banana. It definitely doesn't sit on a weekday like Tuesday, but a rug or a mat are both possible. But in these thousands of texts that maybe a cat sits on somewhere as on something, mat is more likely than rug, and therefore this is the most likely answer. But these systems obviously can make mistakes, but nowadays they are very advanced. The grouping of things happens uh, by the hidden patterns, and there are no labels. When it comes to large language models, they are technically self-supervised, meaning the hidden word is a label, the model makes it for itself. But we won't look in that in depth. And then you have reinforcement learning. It learns by trial and error. There is either a reward or there is a loss. And you have basically the agent that's the player, for example, that plays chess, and you have the environment that's kind of the chess game. And you first have, you always repeat that, and first have a loss, um, and no, it's equivalent, and then eventually you win. And that's kind of it. It can come up even with new strategies that humans haven't come up with, and that's kind of the power of this system. So as you can see here, the first example, sorting emails as spam or not spam. We had this example. This is supervised learning because the data is already labeled. But grouping customers by buying habits, that's a bit different because it is not, because there are probably not labels for that. And it's not clear what kind of groups there should be, and what there are loads of different examples of buying habits, but maybe that if you give enough data from a shop, for example, and you give it to a machine learning system, it will probably figure out who tries to get the sales, who buys things at a certain time, and that's an example for unsupervised learning. A robot who finds the way out of a maze, that's an example of reinforcement learning because it uses trial and error to get better, and that's that's basically how it can improve. Now, if you have, for example, in biology, a scan with malignant skin and maybe cancer cells, that's again an example of supervised learning, meaning the data is already labeled. But um, if you just want to group songs by their similarity, you can just maybe give the song or the song text, and it will find out similarities between that. And chess or Go, this is obviously the most famous example on for reinforcement learning. As you can see on the bottom of the slide, that's kind of the most important summary. Labels, meaning you have the solution already to a certain input value in the training dataset, means it is supervised. Then there are no labels, so no solution. It finds the patterns itself, then it is unsupervised. And if there is a reward, it is reinforcement learning. So what we'll cover during most of this presentation today is regression. This basically means you go from, you have an input sample and you want the right answer to be predicted. This can be either a number that is probably linear regression that we look at, or yes or no, which is logistic regression or classification. And as an example, we'll use a model that can predict the house price based on its size and the number of bedrooms and other input variables features. You probably know how linear functions work. Okay, you probably know how linear functions work, but normally a function, like a function is very neat, but data is not always as neat. So you have data points, you don't have a whole function yet, but you have to find the line that best fits um, those data points. And as you can see, none of them, or maybe one of them, is exactly on the line, and the others are slightly above or below it. And so there is basically no perfect line. Like there is a perfect line, but not one with zero mistakes. So for that, you have basically a normal linear function where W is the slope, how steep it is, or if it goes down, if it is a negative value. X is the input value, so it's the living area X. And Y, or f of X, is the price that we want to predict. It's the feature. Okay. And B is the y-intercept where the function starts. So it's also called, why is it B? That's because it is the bias. So you can shift this linear function, uh, 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 yeah, to be higher, have a higher y-intercept or a lower y-intercept. You have to minimize the gap between the points, the data points, and the line to make it the best possible line. Um, so no line touches every point in real life. And if it touches every point, you might think, oh, that's super good. This model is perfect. But we'll see that this is probably a bad sign if the model can label the training data perfectly. You basically have the cost function. We don't go into detail about that. Here is the formula if you're interested in that. But basically, you draw a square, so you square it. If there is a small gap between between um, between, for example, if you have a distance of, let's say, 2 between data point and the line, then that would be twice as important as like, for example, or let's say uh, having um having something that is double the distance when we square it has 4 times the influence on the cost function, because nothing has to be exactly on the line, and that's okay. But if there are data points that are just not on the line at all, they should have a lot of weight um, in the cost function. So we try to minimize the value of the cost function. And you probably, if you've taken a calculus class, you know we have to optimize the function. And what you see here is the cost function. In this case, it's a quadratic function. Um, and you want to find the minimum. And you probably know that the local minimum of a function is if the first derivative is 0, so the slope of the line is flat. And in this case, it is opened upward because the second derivative is above 0. So to get the best slope, to get to a slope of 0, you have to either derive the cost function. That's possible in this case, but that's not always possible. If you've taken, like, you can derive this function, but in real machine learning, these functions can be extremely big, and it's just not feasible or impossible to do it with these calculus methods. So there are other methods that work. Here's an example that we don't have to look at. Yeah, but we yeah, but we saw one input variable before, but now for the price of a house, there are multiple things that influence it. For example, the number of bedrooms and the living area. So we have two input features, one is called x1, x2, all the way to xn. And when having two features, so bedrooms and living area, you just expand this basic linear function. You multiply the weight of the first input variable plus the weight of the second times the second input variable all the way to n plus the bias. But if we have two features, it is no longer a linear function, but it is a linear plane and in 3 dimensions. So if you have taken vector, if you have had the topic of vectors and planes and stuff like that in a math class, you'll be familiar with that. You can also try to find the best fit plane through the data points. Now, as I said, the normal traditional calculus methods of deriving a function to find the minimum doesn't work usually, so you use something called gradient descent. So it's basically like that. You are on a hill and you know you want to go down, but you basically maybe, let's say your eyes are closed, you can't see where the minimum will be, but you just see or feel the next step goes down, and then you just take this step. And by doing that, you get always closer to the valley. However, there is obviously a problem. It can be that you only find a local minima and not the global minimum. And that's kind of a problem. So you're actually in quite a bad situation. Maybe you would have had to walk upwards a bit, and then it would go down a lot to the global minimum, but you decided to go straight downwards and you landed at a local minimum that is not the best situation for the model. And yeah, as I said, you always take the steepest way down, take only small steps so you don't miss the valley. And we repeat that over and over and over again until you reach the bottom. And yeah, it seems quite tedious and not as elegant, maybe as deriving a function, but it works. Here you see it in 2D, basically the same thing. Alpha is the step size, so how large is your step? And it's very important that it is neither too large nor too small. And I'll explain that later. And as you can see, the W with the star, that is the weight that we want to have. That's the weight we optimize for. And the same goes with the bias. We also have to optimize that with a cost function and then apply gradient descent to it. This also works in 3D. This is kind of not a parabola, but but just the same thing kind of in 3D. So you also take the steepest way down until you're on the bottom of this shape. it works pretty much the same way, but in this case you have two inputs. Now you have to choose the learning rate or the step size alpha. So if you have a too small learning rate, that means it takes a long time to reach the bottom of the function, of the cost function. And that just increases the time it takes to train a model. But if you make alpha too large, it overshoots. Maybe you start here on the white dot and then you go all the way again up because you missed, it was way too large and you missed the minimum. So it should be in the middle ground that allows not to not to overshoot, but still be efficient in getting to the bottom. So we had the example of the living area and the bedroom amount of bedrooms in our price prediction model, but you may realize the living area is just on a completely different scale than the amount of bedrooms. And so the living area has a much higher influence. But that doesn't have to be the case. Maybe the living area and the bedrooms are has the same influence, or it could even be that the number of bedrooms is more important than the area of a building. So this is a problem because first gradient descent chases the bigger numbers and barely learns from x2. So the training process of the model is slow and unstable, and it just doesn't get you the result it should get. And so you have to bring them to the same scale. And you can basically use this formula that is here. You have to input value, then you subtract the average value divided by the by the spread of by the standard deviation, and then you have features that are in a similar range. So you don't have 150 square meters and every rooms, but they are all on the same scale, usually between usually around 0. So you can see here on the left side, x2 is much smaller. It's all grouped together, and x1 has much larger values. And so basically when training, the model thinks, oh yeah, x1 is the more important feature, when it is not the case. So you have to bring them to the same scale. As you can see here, they are in the same range. Obviously, inside this range there are differences, but they are just orders of magnitude lower than if you had the unnormalized data. So we also have to talk about learning and testing of models. You basically have the training data and the test data. And I think you don't have to go in depth, but here is kind of the main idea. If you have a data set, for example, you want to do something in science, for example, diagnosing tumors with computer vision, and you have images, and you usually choose 80% as training data because the model has to recognize why the labels match to the different input images. And 20% are test data. And it kind of always needs a test data set that is new and different to the training data set. Because in the training data set, the model tries to minimize the cost function, optimize weights and biases to fit the training data. But the training data is just a sample of the data that's out there. And it can be that the model doesn't learn the real underlying patterns. It just tries to exactly mimic the test data. And if you don't test it on new data, you don't know if the model actually generalizes or just replicates what it has learned. Now there are kind of two ways that this can go wrong. The first is underfitting. So the model is too simple. You see the dots. I can draw it here. They should be connected with approximately this function, a quadratic function that it is opened downward. But you use a linear regression model. So it tries to fit a line through the data, and it's just simply not gonna work. You see here, these data points, they match pretty good, but there are outliers that just don't match the model at the linear function at all. And you just have to have a more complex model for this situation here. There is another problem, which is called overfitting. So you basically saw, as I showed again, the function should be approximate. Okay, that's not much better, but okay, yeah, it should be about like that. Okay, it doesn't look nice, but you get the idea. It shouldn't exactly match the data points that are shown here, but it should approximate it. And here you just have a too complex model, and therefore it tries to find every single relationship, even if it's just noise in the data. And you have to go the middle ground and really not have underfitting, but also not have overfitting. And overfitting can be seen if the training data, if the model looks perfect on the training data. And as I mentioned before, having a perfect model on training data is never a good sign, because it just means it it didn't generalize, but exactly kind of grew the function through every data point. And if it doesn't work on test data and training data, that's underfitting. Both of them are bad. So we had this example of regression, so predicting the house price, but this is a number. So we use the linear function, but there are often yes or no problems. For example, you want to know, is something a tumor or not? You don't want, yeah, the tumor is that big. You want to know, is it a tumor or not? Should I buy the house or not? Maybe that's also something else. Or is it spam or not spam? And for that, you use classification or a logistic regression. As you can see here, a linear line kind of fits, but it's not the best thing, because there are regions, especially in the middle, where it could be on either side. And there will obviously always be mistakes in this sort of model, but it should be the probability that it's, for example, 0 or no, should be as high as possible when it's no tumor, and as low as possible when it is a tumor. So you need a different kind of function. And this function looks like that. Um, you don't have to know exactly what this function does, but it just looks like an S-curve. And so you see in the left area, it is very confident that if the data point is in this area, it will be no tumor, for example. And if it's far to the right, it is pretty confident that it is a tumor. But if the data point is somewhere in the middle, it can't really decide. It could mean it is a tumor or it isn't. And in this case, you just need to draw a line exactly in the middle and say if it's above 50% chance for a tumor, let's classify it as a tumor. And if it is below 50% chance of being a tumor, you have to classify it as not being a tumor. And this sigmoid function forces values to 0 and 1, and there's kind of no 0.5. Again, there is a weight, there is a bias. The bias shifts it from left to right. For example, if you had 0 in the middle, you could say 50% is exactly at x equals 0, or you could shift it to the right to maybe x equals 1, or to the left, x equals -1. And the weight is basically how steep the function is. As you see here, a steeper function usually means the model makes better predictions. So the 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 range of x input values where it is not so confident is usually smaller than if it is widespread. So it means it is more an ambiguous problem. And as you see, the function looks just like a linear function. Okay. The decision boundary is basically, as I said, you draw a line and a cutoff. So if it's below 0.5, you say it is 0, or if it's above 0.5, it will be yes. Okay. Now, an artificial neuron is basically all that put together, but we don't have to go in depth.